Hello everyone, and welcome to the first session of our online course, Data-Driven Optimization with Groby. We are going to kick things off by exploring the fundamental concepts of optimization. Before we dive into the code and the heavy lifting of Groby, we need to understand the soul of the problems we are trying to solve. This session is titled, Introduction to Optimization Concepts. Our roadmap for today is divided into three main pillars. First, we'll define what optimization actually is and why it has become a non-negotiable tool in the modern world. Second, we will break down the three heavy hitters of the optimization world: linear programming, integer programming, and mixed integer programming. Finally, we'll wrap up with a conclusion and a look at the key takeaways you should carry with you into the next session. In today's industrial landscape, decisions are rarely simple. Take large-scale energy systems as an example. These systems have an incredible number of moving parts, very scarce resources, and goals that often conflict with one another. For instance, how do you minimize costs while simultaneously maximizing reliability and minimizing carbon emissions? When you have that many variables, you cannot rely on intuition alone. You need a structured, mathematical approach to find the right balance. For a long time, business leadership was driven primarily by gut feeling or professional intuition. While experience is valuable, it has significant limits in the face of modern data. Gut feeling often fails because of three things: hidden trade-offs, data overload, and the high cost of trial and error. When you change one variable in a complex system, it often creates a ripple effect that the human brain simply cannot predict accurately. We are currently living through a complexity explosion. We are no longer managing 10 or 20 variables. We are managing thousands, or even millions, of variables and constraints simultaneously. This is where systematic modeling becomes our most important tool. Systematic modeling is the bridge that takes us from the messy, unpredictable real world into a structured mathematical model. By doing this, we move away from guessing and toward structured decision-making. We create a digital environment where we can test every possible scenario mathematically before we ever commit a single dollar or resource in the real world. It allows us to be proactive rather than reactive. Let's take a moment to really define what we are doing here. At its heart, optimization is the science of the best in any given situation. There are millions, sometimes trillions of possible choices we could make. Optimization is the systematic process of finding the single best possible solution among all those options, while strictly adhering to a set of requirements. Think of it as the ultimate balancing act. We are trying to do the most with what we have. This usually manifests in two ways. We are either maximizing something positive like total profit, output, or efficiency, or we are minimizing something negative like cost, waste, or risk. Why is this so vital? Because in the real world, we live in a state of scarcity. Time, money, raw materials, and labor are all limited. If we had infinite resources, we wouldn't need optimization. But because we don't, we have to ensure every dollar and every hour is used perfectly. For example, consider a factory. You have a fixed amount of steel, plastic, and labor hours. You can make product A, which has a high profit but uses a lot of steel, or product B, which has a lower profit but is very fast to assemble. Which combination of A and B creates the most profit without running out of steel or overworking your staff? That is a classic optimization scenario that we solve by maximizing a profit function subject to resource constraints. To make this less abstract, let's look at how you are already an optimizer in your daily life. First, consider route planning. Every time you open a navigation app like Google Maps or Waze, you are interacting with a complex optimization solver. The objective is to minimize travel time. The decision variables are the different turns and highways you could take. The constraints are the speed limits, one-way streets, and current traffic conditions. The app calculates the optimal path through a massive network of possibilities in milliseconds. Second, think about personal budgeting. You have a finite amount of monthly income that is your primary constraint. Your goal is to allocate that money across expenses like rent, food, and utilities, while maximizing your savings or your quality of life. You are making trade-offs. If I spend more on dining out, I must spend less on my savings goal. Finally, consider task scheduling. You have exactly 24 hours in a day. You have a list of 10 tasks, each with a different deadline and a different level of importance. You are optimizing your productivity by deciding the order in which you tackle these tasks so that you meet all your deadlines without running out of time. In each of these cases, you are intuitively doing what Groby does mathematically. You are finding the best possible outcome within the limits of your reality. Let's get right into the mathematical programming toolbox. Mathematical programming is the formal framework we use to translate a complex, real-world decision problem into a set of precise math equations. It is the language that allows us to communicate a business problem to a computer so it can find the best possible answer. Every model in this toolbox is built using three fundamental components. First, decision variables. These represent the choices you need to make, the knowns that the model will solve for. Second, the objective function. This is your target. It mathematically defines your goal, whether you are aiming to maximize total profit or minimize total operating costs. And third, constraints. These are the rules of the game. They represent your physical limits, such as your total budget, machine capacity, or delivery deadlines. Once we have formulated our problem using these three elements, we use a solver to find the answer. For large-scale, industrial-strength problems, we rely on Groby. Groby is a high-performance engine that uses sophisticated algorithms like the simplex method and advanced mixed-integer techniques to search through millions of potential solutions in seconds. Essentially, the solver is the bridge that takes us from a complicated real-world mess to a mathematically provable optimal solution. Let's look under the hood of those three components. First, the objective function. This is a single numerical value that represents your success. If you are a logistics manager, this might be the total cost of fuel. If you are a hospital administrator, it might be the total wait time for patients. The optimizer is laser-focused on making this single number as small or as large as possible. Second, the decision variables. These are the knowns. We often categorize them into two types. Continuous variables are for things that can be fractions, like the amount of electricity or liters of fuel. Integer or binary variables are for yes or no decisions, like should we open this warehouse, or for things that must be whole units, like number of airplanes to purchase. Third, the constraints. These are the rules of physics, law, and logic. You might have a constraint that says the total weight of the cargo must be less than or equal to the truck's capacity, or all customer orders must be filled. These constraints carve out what we call the feasible region. Any point inside this region is a possible answer. Any point outside it is impossible because it breaks a rule. The optimizer's job is to search the very edges of this feasible region to find the absolute best point. Now, let's look at how we express this to the computer. Every optimization problem, no matter how complex, follows a generic mathematical structure. We seek to maximize or minimize the function f of x. Here, f is our objective, and x represents our vector of decision variables. But we don't have total freedom. We are subject to the condition that the function g of x is less than or equal to b. In this part of the formula, g of x represents our constraints, the way our variables interact, and b represents our limits, such as our total budget or total available hours. Finally, we often include a condition that x must be greater than or equal to 0, because in most real-world problems, you cannot have a negative amount of a resource, like -5 gallons of oil or -2 employees. This simple-looking structure is the universal language that allows Groby to understand almost any business problem on Earth. Visualizing this provides intuition into our model. Imagine a graph with an x-axis and a y-axis, where x is the amount of product 1 we make and y is the amount of product 2. Each of our constraints, like our budget or our labor hours, acts like a wall on this graph. One constraint might be a diagonal line that cuts across the middle. Another might be a vertical line. The area where all these walls overlap creates a shape, often a polygon, which we call the feasible region. Every single coordinate inside that shape is a valid plan that doesn't break any rules. However, we don't just want a valid plan, we want the best plan. Our objective function can be visualized as a slope or a direction of improvement. We want to push our solution as far as possible in that direction until we hit the very edge of our shape. Mathematically, for linear problems, the best answer will always be at one of the corners or vertices of this shape. Gurobi's algorithms are designed to efficiently jump from corner to corner until they find the one that provides the highest or lowest possible value. This is how we turn a geometric shape into a perfect business decision. It is important to remember that mathematical programming is not a silver bullet. It is the perfect tool when your goals and constraints are precise and quantifiable. If you need a solution that is provably the best possible option, Gurobi is your primary choice. However, if your goals are purely qualitative, or if you are dealing with a black box system where you don't actually know the underlying math, you may need to look toward heuristics or simulations. In the professional world, we often use a hybrid approach, using exact optimization for the core logic and heuristics to handle the messier, less defined parts of the problem. To understand the stakes of what we are learning, we have to look at what happens when optimization systems fail. The Southwest Airlines meltdown in late 2022 is a sobering case study. During a massive winter storm, Southwest had to cancel nearly 17,000 flights over 10 days, leaving 2 million passengers stranded and taking a financial hit of over $700 million. Why did this happen? It wasn't just the weather. It was a failure of their SkySolver crew scheduling system. As the disruptions piled up, the system became overwhelmed. It reached a point where it could no longer repair crews to aircraft. Because the optimization engine couldn't scale to handle the sheer volume of changes, pilots and cabin crews were left out of position, which triggered a massive, uncontrollable cascade of cancellations. This wasn't a failure of the pilots or the planes, it was a failure of the optimization infrastructure to handle a high-stress scenario. The lesson here is vital for anyone using Gurobi or any other solver. Even a world-class, multi-billion-dollar airline can be paralyzed if its optimization engine can't scale or recover from a shock. When we build models, we aren't just looking for the best answer in a perfect world. We are building systems that need to be robust. Your model needs to be formulated in a way that allows the solver to find answers quickly, even when the data starts changing rapidly. As we move forward in this course, we will focus not just on finding a solution, but on formulating models that are efficient and resilient under pressure. As we close out our first chapter, let's recap the 3 most important points. First, complex decisions require a structured, mathematical approach. Gut feeling is a great starting point, but it cannot navigate the complexity explosion of modern industry. Second, a model is always a combination of variables, constraints, and an objective. Together, these lead us to the best solution. And third, industrial-grade solvers like Gurobi are what turn these abstract models into real-world action. But as we saw with the Southwest lesson, these models must be designed to be robust and scalable. If the math is solid, the business is solid. Now we move into Chapter 2, where we define the specific classes of problems we will solve. We categorize these based on 2 factors: linearity and variable type. For a model to be linear, all expressions must be simple combinations. In word form, this means y equals m times x plus b. You cannot have variables multiplied by each other or raised to a power, like x squared. The second factor is the variable type. If your variables are continuous, meaning they can be any fraction like 1.5, it is a linear program. If your variables are integers, meaning whole numbers like 1, 2, or 3, it is an integer program. When you have a combination of both fractions and whole numbers, we call it a mixed integer program. Understanding these differences is key, because while LPs are incredibly fast to solve, MITs are much more common in business, where you have to make yes or no decisions or count whole units like trucks or employees. We are now entering the heart of the course. In this section, we will break down the big three categories of optimization: linear programming, integer programming, and mixed integer programming. While they share the same DNA variables, objectives, and constraints, the specific rules of each class determine how we solve them and what kind of real-world problems they are best suited for. Let's start by looking at the systematic process of solving a linear programming problem. Solving an optimization problem is a disciplined, 8-step process. It starts with step 1, defining the goal. You must decide exactly what you are optimizing. Are you minimizing cost, maximizing profit, or perhaps minimizing carbon emissions? Step 2 is identifying your decision variables. These are the quantities you can actually control. In step 3, you translate your goal into a mathematical objective function. Step 4 is listing your constraints. These are your resource, policy, or logic limits. Remember, for an LP, these must all be linear expressions. In step 5, we add our domain rules, such as non-negativity, meaning your variables must be greater than or equal to 0. Once the model is built, step 6 is choosing your approach. For simple two-variable problems, you can use a graph, but for anything larger, we use solvers like Gurobi, which utilize the simplex or interior point methods. Finally, in steps 7 and 8, you run the solver, verify that the solution is feasible, and perform stress tests or sensitivity analysis to see how the result changes if your input data shifts. This ensures your solution isn't just mathematically correct, but practically useful. To illustrate how linear programming works in practice, let's look at a classic production planning problem. Imagine you are running a factory that manufactures two different products, which we'll call product X and product Y. To make these products, you rely on two specific machines, machine A and machine B. Every unit you produce consumes a certain amount of time on these machines. Now, here is where the challenge begins. You aren't starting from zero, you already have some existing stock in your warehouse. However, you also have a forecast for customer demand that you must meet by the end of the week. You are facing three main pressures. First, your machines have a strictly limited number of hours available. This is your capacity constraint. Second, you must produce enough to satisfy your customers. This is your demand constraint. And third, your management has set a specific goal. They want to maximize the total number of units sitting in your inventory at the end of the week. Your job is to find the sweet spot. How many units of X and how many of Y should you manufacture to hit that maximum inventory level without overworking your machines or failing your customers? Don't worry about the specific minutes or hours just yet. On the next slide, we'll see how we translate this story into a mathematical map. Now, let's translate that story into the language of math. First, we define our decision variables. Let make X be the number of units of product X we produce, and make Y be the number of units of product Y we produce. Next, our objective function. We want to maximize our total ending stock. In word form, our objective is to maximize the quantity 30 plus make X plus the quantity 90 plus make Y. Since the 30 and 90 are constants, this is mathematically the same as simply maximizing make X plus make Y. Finally, we have our constraints. For machine A, the total time used must be less than or equal to 40 hours. Since our processing times are in minutes, we convert 40 hours into 2400 minutes. So, our constraint is 50 times make X plus 24 times make Y is less than or equal to 2400. For machine B, we have 35 hours, or 2100 minutes. The constraint is 30 times make X plus 33 times make y is less than or equal to 2100. We also add our demand constraints. 30 plus make x must be greater than or equal to 75, and 90 plus make y must be greater than or equal to 95. This is how we take a complex business policy and turn it into a clear mathematical map for Gurobi to follow. Now, how does Gurobi actually solve that map? For linear programming, the most famous method is the simplex method. Think back to our graph of the feasible region, that shaded polygon representing all possible solutions. As we discussed earlier, in a linear problem, the optimal answer is always going to be at one of the corners or vertices of that shape. The simplex method is a very efficient corner-to-corner search. It starts at a starting point often, where all variables are 0, and then it looks at the adjacent corners. It asks, if I move to this next corner, will my objective function improve? If the answer is yes, it pivots to that new corner. It repeats this process over and over until it reaches a corner where every neighbor is worse than the current position. At that point, it has mathematically proven that it has found the optimal solution. While this sounds like it might take a long time, the simplex method is incredibly fast, even for problems with thousands of corners. While the simplex method travels along the outside edges of our feasible region, there is a second major way to solve LP problems, the interior point method, sometimes called the barrier method. Instead of jumping from corner to corner, the interior point method takes a shortcut through the middle of the shape. It uses a mathematical barrier function to stay away from the walls of the constraints, following a smooth curve toward the optimal area. Think of simplex like a hiker following a trail around the base of a mountain to find the peak, while the interior point method is like a helicopter flying directly over the center to land on the summit. Both will eventually find the same optimal point, but the way they travel through the data is fundamentally different. You might wonder why we need two different methods. The answer lies in the personality of your data. The simplex method is excellent when you need to perform warm starts. If you solve a problem, change one small constraint, and want to solve it again, simplex can start from where it last finished. This makes it the go-to choice for the internal nodes of a mixed integer search. The interior point method, on the other hand, is a powerhouse for massive or very sparse problems. It often requires fewer steps to reach the answer than simplex does when the scale of the problem is enormous. The good news is that you don't usually have to choose. A solver like Gurobi is intelligent enough to look at your model and automatically select the method that will give you the fastest result. In some cases, it will even run both at the same time in the background and simply return the answer from the one that finishes first. Up until now, we've assumed that our variables can be any fraction like producing 5.7 units of a chemical. But in the real world, many decisions are indivisible. You cannot open 0.42 of a warehouse. You cannot hire 1.7 pilots. These are yes or no logic choices, or what we call whole unit counts. If we use a standard linear program for these problems, the math might give us a result that is technically optimal but practically meaningless. This is why we need integer programming, or IP. We take our same linear model but add a special rule: certain variables must belong to the set of integers. If the LP wants to pick 2.7 pallets, the IP solver will force it to choose either exactly 2 or exactly 3. This small change makes the problem much harder for the computer to solve, but it makes the solution actually useful for your business. We generally categorize these problems into 3 buckets. First, pure integer problems. In these models, every single decision variable must be a whole number. This is common in crew scheduling or job-to-machine assignments. Second, mixed integer problems. These are the most common in industry. Some variables are integers like should we turn this machine on, while others remain continuous, like how much electricity should the machine consume. Third, a special and very powerful case called 0-1 integer programming, or binary programming. Here, variables are restricted to exactly 0 or 1. This is the perfect mathematical tool for yes or no choices. 0 means no. Do not fund this project, and 1 means yes, greenlight this initiative, as we will see. This allows us to model incredibly complex logic and strategy. This brings us to one of the most common and difficult challenges in business: strategic resource allocation. Imagine your team has a strictly limited budget, a hard cap on capital that you cannot exceed. You have multiple potential initiatives on the table, each with its own cost and its own expected value. The decision-making challenge here is the all-or-nothing rule. In this course, we call this indivisibility. You cannot fund 60% of a project. It either happens or it doesn't. This creates a massive combinatorial problem. As you add more projects, the number of possible combinations to test grows exponentially. Why do we care about this in this course? Because this is where standard linear programming fails. If you use a simple continuous model, the math will likely tell you to fund a fraction of every project to use up every cent of the budget. But in the real world, that's impossible. By using 0-1 binary variables, we can force the model to respect the reality of yes or no decisions. This allows Groby to sift through thousands of project combinations to find the exact subset that creates the highest total economic value while staying within your budget limits. Once we apply those binary rules, the results become clear. In our example, the solver identifies a specific optimal subset. It doesn't just look at the projects one by one, it looks at how they fit together to fill the knapsack of your budget. On this graph, you see the red X located at the point where we have used 9.5 million of our 10 million euro budget to generate 13.4 million in value. This is represented by a binary label 1, 1, 0, 1. This means projects 1, 2, and for our greenlit, while project 3 is dropped. This is the power of 0-1 programming. It gives you a definitive, executable list of go or no-go decisions that are mathematically guaranteed to be the best possible use of your capital. Now, how does Groby actually solve these difficult integer problems? It uses a method called branch and bound. Since we can't just round off a fraction, we use a divide and conquer strategy. First, we solve the LP relaxation. We ignore the integer rules and let the solver treat everything as a fraction. This gives us an upper bound, the theoretical best we could ever do. Then, we branch. We pick a variable that should be an integer but came out as a fraction, say 0.7, and we create two new subproblems. In one, we force that variable to be 0. In the other, we force it to be 1. As we build this tree of possibilities, we bound each branch. If a branch has a theoretical value worse than a solution we've already found, which we called incumbent, we prune it. We cut it off and never look at it again. This allows Groby to mathematically ignore millions of bad options and focus only on the promising ones until no open nodes remain. This visualization shows what that search looks like inside Groby's memory. It looks like an upside-down tree. Each node represents a smaller version of the original problem with more restrictions added. By systematically exploring this tree, Groby can provide a guarantee. When the search is finished, the last incumbent solution is provably optimal. This means we don't just have a good answer. We have the best answer that exists in the universe for that specific model. This level of certainty is exactly why industrial-grade solvers are worth the investment. In the real world, most problems aren't just pure yes/no or pure fractions, they are a mix. This is mixed integer programming. Consider a logistics network where you have 3 distribution centers and 3 regional markets. You have 2 different types of decisions to make. First, the integer decision: should you even pay the fixed cost to open a specific distribution center? Second, the continuous decision: if a center is open, how much product should you ship through it to minimize costs? This hybrid structure is what makes MIP the workhorse of modern industry. You are balancing fixed costs, the one-time cost of an action, against variable costs, the cost that grows with every mile or every ton shipped. Now, let's look at how we translate our logistics story into a mixed integer model. This is where we see the interplay between two different types of mathematical variables working in tandem to solve a real-world problem. First, we define our decision variables. In this model, we have a two-tier structure. We use binary variables represented here as yj to handle the discrete yes or no decisions. These tell the solver whether or not to open a specific facility. Alongside these, we have continuous variables represented as xjz, which represent the actual volume of goods flowing from a warehouse to a customer. This allows us to track not just if we are using a route, but exactly how much product is moving through it. Our objective function is built to minimize the total yearly cost. Mathematically, this is expressed as the sum of all fixed opening costs multiplied by their respective binary flags, plus the sum of all individual shipping costs multiplied by the volume of goods moved. This captures the fundamental business trade-off. Is it cheaper to pay a high fixed cost to open a warehouse that is strategically close to a customer? Or should we save on that fixed cost and pay more in variable shipping fees from a distant location? The solver weighs these two components against each other to find the absolute cheapest total. Finally, we have the flow balance constraints. These ensure that the total amount of product leaving a warehouse does not exceed its capacity, and more importantly, that the total amount arriving at each destination meets the customer's specific demand. By combining these logical binary switches with continuous flow equations, Groby can navigate millions of permutations to tell us exactly which warehouses to open and exactly how to route the product. To speed up these complex searches, Groby uses a technique called cutting planes. Sometimes the feasible region for an LP relaxation is too loose. It contains a lot of empty space that doesn't have any real integer points in it. A cut is a new linear equation that Groby adds automatically during the search. It acts like a surgical strike, slicing away parts of the feasible region that contain fractional solutions but leaving every valid integer solution untouched. This tightens the model, giving the solver something to bite on. It leads to fewer nodes in our search tree and a much faster proof of optimality. While modern solvers generate hundreds of these cuts behind the scenes, a high-quality model is one that is already tight enough for these cuts to be effective. As we wrap up our discussion on problem types, keep these three lessons in mind. First, same recipe, different rules. Every model starts with a linear objective and constraints. You only change the flavor of the problem by adding continuous variables for fractions or binary flags for yes or no decisions. Second, LP gives you fractions, but MIP makes them real. Use MIP when your business reality involves whole units or indivisible choices. And third, good formulation is 90% of the job. A well-structured model is much easier for Groby to solve than a messy one. Your goal as an optimizer is to give the solver a map it can navigate efficiently. If you want to dive deeper into the mathematics of the simplex method, branch and bound, or cutting planes, I have provided several high-level resources here. I particularly recommend the mid-OpenCourseware lectures on linear programming and the Stanford Notes on Localization Methods. These provide the deep mathematical proofs behind the algorithms we discussed today. In our next session, we leave the theory behind and get hands-on. We will explore exactly what Groby can do, learn how to install it, and set it up in your Python environment using the Groby package. We will write our very first model using the model function and learn how to add variables and constraints in code. I look forward to seeing you in session 2 as we start building these models for real. Thank you for your time today.